So I will look now at the matrix representation for the perspective projection and also for the orthographic projection. First of all, to get started, we need to fix our coordinate system. We conveniently choose the pinhole as our origin of our coordinate system. And as before, we have the x-axis going right, the y-axis going up, and the minus z-axis into the scene. In the slide here, I use a focal length. The focal lengths I write down as tau. I don't use any mirroring, so I put the image in front of the pinhole. This way, it's right side up and left and right are not mirrored. The perspective projection can be really quite simply put into homogeneous coordinates, exploiting that fact of the homogeneous coordinate, the division here. So this simple matrix here with these three entries, 2 times the focal length, here at the 1, 1 position and at a 2, 2 position, and then a 1 here in the third column of the matrix in the homogeneous position will do the trick. So how does this work? For this, we have to look at what would happen if we have a point. So if we have a point here, the point is at AX, AY, and AZ. We put a 1 here as usual for our homogeneous points. And if we multiply this point here by such a perspective projection matrix, what we get out is that here in X we get tau times AX, in Y we get tau times AY, and here in the homogeneous coordinate we get AZ. The Z coordinate doesn't really matter because we're projecting into 2D, but I keep it here just for now to have all zeros in here. So how do we know what the Cartesian coordinate is then of this image point? Well, we have to divide by the homogeneous coordinate, just as before. Now, the only difference here we have now a value other than 1, but the rule still stays the same. So the Cartesian coordinate for x is tau times ax divided by this homogeneous coordinate az. And when you look at this, this is exactly the pinhole relationship we talked about before. It's the similar triangles, right? So the ratio between the focal lengths and the scene depths is the same as the ratio here of the image x versus the scene x. So this is the x coordinate, the y coordinate works exactly the same. In reality, of course, we don't have any z here in a camera. Now let's look at what we do for our rendering. And this is mainly what do we do with that z coordinate, which we know that for the image we don't need it, but for rendering we would like to have it around. Why do we want that z axis around? Because actually during rasterization we want to decide which triangle, or really which pixel, is in front of another pixel in our scene. And for this we need to know where they are in Z, right? We need to know what's closer to the camera versus what's further away. For this reason we will keep that Z axis around. We just need to know what do we make this Z coordinate to be after the perspective projection. The choice in OpenGL is that the focal length corresponds to the distance to the near plane. So when you set the near plane in GL frustum, that near plane is also setting the focal length. Here I'm putting in here the near plane instead of tau now, which is our focal length. And then we have to decide what to do in the third row here. What's done in OpenGL and WebGL is to set them as follows. So we made the point 3, 3 here becomes near plus far, and here this entry is in the third column for the homogeneous coordinate becomes minus NF. Now, why is that? In order to see how this works is we pick a point here on the near plane, right? So it has some x, it has some y coordinate, but its z coordinate is n, so it means it's on the near plane. Now we said before that the near plane should become the image plane. So this point should not move away from the near plane for this to work, because the near plane is the image plane, so things in the image plane image to the image plane. So we can check that by multiplying this point here with this projection matrix. So if I do this, well, what do I get out? I get here n times ax, I get here n times ay, and then this third row here, when you look at this, I multiply n times n, gives me n squared, plus nf, and then I have here from the back, I have minus nf, so that cancels out, so I'm left with n squared. And then I have here the homogeneous coordinate, as before, it multiplies the depth, so the n here, so the result is n. And clearly, as you can see, if I'm homogenizing this point, i.e. dividing by n, getting Cartesian coordinate, then a point which started out on the near plane ends back up on the near plane because we're going to divide n squared by n. Can also do this with a point on the far plane. So here I say, well, it has some x value, has some y value, but it sits on the far plane f. And when the point sits on the far plane, its z coordinate after perspective projection ends up still being on the far plane. Because when you look at this, n multiplies ax, n multiplies ay, and then here, taking this f and multiplying this with n plus f, I get n times f plus f squared, and then comes a minus nf from here, it cancels out again, so I'm left with f squared. I have here as this distance in the homogeneous coordinate, f times 1 gives me f, so I have here f. So in other words, with this choice of parameters for this imaginary, well, I shouldn't say imaginary, but, you know, just in our minds, z coordinate after the projection, the points at the near plane stay at the near plane, and at the far plane, they stay at the far plane. So the z here is unchanged. Before this it's n or f, and that's what it is after. When we look at all points along the z-axis, not just at the near plane and far plane, then things look a little bit different. So here I have an example, or I drew out this example here, where n is equals 1 and f is equals 10. It's just this example. Down here I have my scene, my z-coordinate. So my z-coordinate in the scene starts at, well, strictly speaking, minus 1, 2, 3, and so forth to minus 10. So here 1 to 10 is my scene depth. Now with that formula which we just looked at, we said that the far plane 10 maps to 10. Right? The far plane stays unchanged. And sure enough, if I go up here, see where this red curve is, and I go to the side, I get a 10 here. And then the near plane maps to the near plane. So if I get here at 1, I come out at 1. So the relationship between the set in the scene and the set after the perspective projection is not linear. It makes a curve. So even so the two endpoints, the near and far plane, are the same, in between here we have this relationship, which is a 1 over z relationship. That means that when we have here the value 2 from the scene maps to a 6, the value 3 maps to over 7, and so forth, while the value 9 is basically nearly the same as the value for 10. Right? And this comes from the fact that we have this perspective divide.